So hello again. Tonight we're going to talk about small satellite ride sharing. This is something that one of the Broward Astronomy members suggested last week. Ought to be interesting. So I said, sure, why not? And as usual, I went down some fairly deep rabbit holes and found there's lots of programs out there, both commercial and educational, and some of them are government funded, some of them are private funded. So this is the old way of launching satellites. If you have a larger satellite, then you want the rocket all to yourself and you're willing to pay for it. Currently, if you want to launch a SpaceX Falcon 9 rocket to low Earth orbit, you can launch up to 25 tons or 22,000 kilograms, and it will run you a cool $69.75 million. Now, I don't know whether that includes tax, tag, and title, if that's the total price or if there's incidentals, FAA permits and stuff. I don't know if that's extra, but that's gotten down quite low because it used to be hundreds of millions of dollars for NASA to get anything launched, and then the actual satellite would cost you millions more. The last NASA crewed capsule that was the preliminary for what we're going to be sending back to the moon, that was $1 billion for the first launch, and none of it was reusable. The capsule came back, but the rest of the rocket was all throwaway. If the satellite is heavy or very large, or you need to put it into high orbit or geosynchronous, geostationary, or polar, you're probably not going to be sharing the launch vehicle with any other satellites, especially if your satellite's so big that even SpaceX can't reuse like the booster because it's just too far out at sea. If it's a Falcon Heavy, maybe reuse the side boosters, but can't reuse the center booster because it's just too far away. They don't have enough fuel to get back. Currently, the fate of second stage and third stage boosters is all throwaway. It's just not economical for them to have enough fuel and make that upper stage big enough to get it back to the point where they can even land it on a drone ship in the ocean. So what we're going to focus on is the smallest of satellites, not the big stuff. That's a business unto itself. Small satellites, or how low can you go, so to speak. They're going to be in short-lived orbits. So these are the lowest of low Earth orbiting. The orbits last less than a year, maybe only days, maybe only months. The low Earth orbit is to the bottom side of LEO, the bottom side of low Earth orbiting. So about 500 miles or 800 kilometers. Basically where you can have multiple satellites launched on a single rocket, whether the total number of satellites allows the booster to be reused or not. So let's introduce the concept of ride sharing. If the altitude you want to send your satellite to is no higher than low Earth orbiting or LEO, if the payload of your satellite is less than the rocket can actually lift, hundreds of pounds, 1,000 pounds, as opposed to tonnage, if it'll easily fit within the fairing, that's that white sort of widened clamshell there at the top. If your satellite will easily fit in there with lots of room left over, it seems wasteful to spend $70 million for your one little satellite to go up. Your satellite might even not cost $70 million nowadays. So ride sharing is a new business where you have a rocket that is capable of launching heavy payloads to low Earth orbit, and you stuff it full of a bunch of smaller payloads, and then you divide up or amortize off the cost of getting the entire rocket up to all the different payloads based upon their weight, and you sell that as a business. So now you can get smaller payloads into low Earth orbit for far less than many millions of dollars. Now, who provides the ride sharing service? Well, it might be, the likes of SpaceX, but SpaceX now has so many ride sharing customers, it's too much like work for them to manage all those small business interactions. So they actually outsource blocks of ride sharing. They'll say like, okay, we've got a launch coming up and we can allocate 1,000 pounds or 1 ton to an outsource company, and they'll go sell all the lighter weight stuff and then book it as one collective sort of modular launch off of that. The idea is to amortize the costs of a launch such that even smaller size payloads, smaller satellites can be launched amongst others instead of doing it exclusively, which is too expensive. But how small is a small satellite? The generic term is SmallSat or small satellite, and they range from a small number of kilograms, single or double digit number of pounds, cube size, sort of oversized Rubik's Cube size, to sort of elongated bread box kind of thing. The typical satellites that you would launch, those are the bigger, heavy ones. Those are not out of focus. Small satellites, they come in smaller and smaller and smaller and smaller varieties. So when they started out, it was small satellites, basically a long breadbox size satellite. And then they went into this, if you kept the same horizontal and vertical dimensions, but shrunk the depth down, you now have cube satellites. It's the same width and length, but also the same depth. So they were 10 centimeters by 10 centimeters by 10 centimeters, or 3.9 inches on a side, a half-length small sat. Those are called CubeSats. And the basic one is called a 1 unit or 1U CubeSat. But that got to be like, we can do better than that. So they came up with something called microsatellites or microsats. Those are even smaller than CubeSats. So think of it like it's a 1/4 size 1U CubeSat. But then as technology advanced, as the sensors, the solar cells, the batteries, the propulsion, as all of that advances, you get smaller and smaller and smaller. So CubeSats to microsats to nanosats to picosats. And people were saying nothing's going to get smaller than pico. And then they actually designed circuit board satellites. So think of it as, if I make a printed circuit board and they put all the chips that I need on that circuit board, and then on the back side of the circuit board, I put the solar cell, and underneath the solar cell, I put the battery, I now have something sort of, how small would that be? About double the width, double the height of a piece of chewing gum and half the length. And that's actually a satellite. It's called a silicon sat, or, the whole satellite is done in silicon, but it's actually chips put on a circuit board. It's a double-sided circuit board. These are very short-lived, probably lasting only a day or two, but they don't just send up one of them. They actually send them up in little swarms. So when they eject them out, they sort of spew them out, and they stabilize their orientation, given all the electronics they have on board, so they can all face in a certain direction as an array. So you can do like radio array silicon sats. You can do energy measurement silicon sats. It's fascinating how small they're going with it. One of the silicon sats that they've been working on is the solar sail test flight. So this is something that's, the body of the satellite is very small, and then it opens up into a giant mylar sail that's a few meters across, and then the pressure of sunlight pushes it, and that's how they confirmed on orbit that, hey, sunlight can work as a solar sail. Don't ask how they turn it around and go the other direction. You can't tack in space. There's no water. But a single satellite can launch a lot of these. So even smaller rockets can launch a bunch of these silicon sats. So you don't need the largest of all rockets to do this. Even smaller rockets can do it. So here's what they call standard sizes. This is back when they believed that nothing's going to get smaller than a CubeSat. So you can see on the left the small one, 10 centimeters by 10 centimeters by 10 centimeters, the 1U CubeSat. And then you've got the longer in one direction, longer in another direction, longer in two directions, and even bigger. So the small satellites were getting bigger. So on one end of the spectrum, you've got small satellites getting bigger because they can make them lighter weight with better technology nowadays. So they might have more sensors, more radio capability, more longer duration batteries, a little more fuel for navigation. So the 49 cubic centimeter satellite might last for a few years instead of a few months. Whereas the 10 centimeter, the 1U CubeSat, might be good for a few months. So if you say, I want to do a shared, ride shared launch because it's cheaper. When can my satellite go up? Get in the queue, so to speak. If a Falcon 9 can be launched every other day for their own satellites, then why can't they launch a shared ride satellite every other day? It's because you might have 100 different satellites on board the one rocket, and you got to get all your ducks in a row before you can launch it. So there's a lot of things you have to go through in order to get your small satellites all in time on the rocket. So they're only going to launch a large quantity rideshare rocket launch about every 3 to 6 months. So it gives smaller companies a bigger window to get their satellite on board, but you have to have outside companies coordinating with other outside companies, coordinating with the rocket launch company, and then getting the approvals from the FAA for the launch and the FCC for the radio communications. And then on the day of the launch, you've got to get weather to approve by FAA and NOAA. So you got to get all these ducks lined up before you can push the button and launch 110 satellites all at once. But if you can pack it full with 110 satellites, and most of them are not the smallest of satellites, they're all sort of 2U size CubeSats, then you can make a lot more money than the actual cost of the launch of the rocket. Good profit margin that. So here's the next step. If you want to save even more money, don't launch your satellite directly on a rocket. Put your satellite on board another launch vehicle that is carrying cargo. So on board the International Space Station, they brought up a module called a deployer from a company called NanoRacks, and they attached it to the end of the robot arm. And inside the deployer, it was sort of spring-loaded a bunch of satellites. And they would grab this thing out of the cargo bay of a cargo rocket on the end of the robotic arm, point it off at a certain direction, and then they'd activate the electronics, and the springs would go patooey, 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 and spit out little satellites, that's kind of like even cheaper. There's no actual launch vehicle. You're riding on a capsule that was going to get launched anyway. It's just a little work for the ISS astronauts to do. But they took that to the next level. NanoRacks, the company that made the deployer, they said, well, what if we could actually carry the satellites up even smaller and carry them inside the capsule? So if they had like a holder inside the capsule, they could carry the deactivated satellites, not in the cargo area, but actually inside the cargo capsule or even inside of a crew capsule. But how would you get them out into space? You'd need an airlock. So they built a special purpose airlock for deploying CubeSats. So you dock your capsule with the ISS, you get out of it, your CubeSats, you load them into the deployer, and then you seal the back door on the airlock, and then you open the front door on the airlock, and you patooey, 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 you eject your CubeSats, and then you close the outer door, open the inner door, and then you take the deployer out, and you can reuse it for next time. So that's like piggybacking on ride sharing. But they found another purpose for it. They made a module that can be ejected, and you can pack garbage from the ISS into the deployer, and you can eject the garbage from the ISS into a short duration burnup orbit. So they actually made a second use for the deployer and the airlock to like open the door, put the garbage in, shut the door, open the outer door, boom, out goes the laundry. And they can burn up garbage from the ISS. So if I was a small satellite company or some students and I wanted to launch something on a ride share, let's say I went to SpaceX and said, hey, how much would it cost? On SpaceX's website, they actually have a ride share estimation calculator. I'm sure there's some, aftermarket dealer add-ons and stuff, but it'll actually tell you what it will cost based upon the weight of your satellite. Now, if you don't want to get your satellite launched any sooner than December of 2024, which is the next available rideshare launch, that'll be Transporter 12, I think. If your satellite is less than 50 kilograms or 110 pounds or lighter, then the minimum shared launch cost for you would be $300,000, which still sounds like a lot of money. So if you were even lighter than that, you could probably go for an outside company that would resell that slot on SpaceX at a lower price per satellite for even smaller satellites. So it may not even cost you 300,000. Collectively, the outside company might be paying SpaceX 300,000, but if you only had 100 pounds total to launch over 20 different companies, then you could make a rack that would launch all at once 20 satellites, and then they would spit out from there. So middlemen, what is the largest port position on a rideshare for SpaceX? Turns out to be 831 kilograms or 1,828 pounds. So whenever you see one of these transporter launches by SpaceX, you'll see a bunch of little tiny satellites and a couple of big ones. The couple of big ones can be no larger than 1,828 pounds. But if you're just calculating things out, the total Falcon 9, if you wanted it exclusive, is that 69.75 million. If you just wanted to launch 110 pounds, that's 300,000. That's a bargain to get your satellite into low Earth orbit. If you want to do some scientific research or some specific purpose commercial observations or something, or you wanted to prove out some space technology, that's cheap. Just remember the first NASA Artemis launch was $1 billion, and the only thing that was reusable was the capsule. If I wanted to launch a satellite and I wanted to go through one of these middlemen, what would I have to know about? There's there's kind of like an enormous checklist of things you have to think about. You want to build your little, let's say, a 1U CubeSat. What are you going to build it out of? I'll just get some steel bars and girders, and no, you don't. It's got to be a certain alloy of aluminum. It's got to be sturdy enough to take all the vibrations and stresses of launch, but it's got to be lightweight enough to not be heavy, and it can't be reactive. So you want it to fully melt away and dissolve away as it goes back through reentry. So you don't want your metals to be too hard. And how are you joining the cross members? Are you using welds? Are you using fasteners? What kinds of fasteners? Because that vibration can make like nuts just unwind. So you may have to have the bolts that have the hole drilled through them, and then you have a little Carter pin that keeps the nut from unwinding. Or you may have to have nylon threaded nuts that like are self-locking, and then you have the Carter pin after that. So you have to think about how the thing is assembled. Okay, let's say you get it up there. It just gets shot out into space. What direction do you want it pointing? Well, you have to know sort of which way is up, which way is the sun at all times. And Earth is down that way. Or if you want to do space is out that way. But if you want to point at a particular star, you need to know how to negotiate your orientation and your position. What are you going to use for power? If this thing's going to be up there for a few days, you might want some solar cells. You might want to recharge your batteries. Because remember, if this thing is in low Earth orbit, it's going from sunlight to dark to sunlight every 45 minutes. So it's going to be in darkness for 45 minutes. Have to think about that. If you are up there and you need to reorient yourself to point at something, what are you going to use for propulsion? What kind of fuels you're going to use? You need to make sure it won't accidentally go boom, because if you're on board a shared launch vehicle and you have something go wrong with your fuel, you don't want to take out the entire rocket and all those other companies' payloads. What about communications? If you want to get your data down from your satellite before it burns up, you need to communicate down to Earth. You need to be able to do command and control. If you want your satellite to point at one thing and then point at another thing, you need to be able to talk to it, command and control. And there was a NASA launch. They're doing kind of a rideshare thing, and it was on a Falcon 9, and they don't think about this thing. The satellite was on board the Falcon 9 inside the clamshell, the fairings. And as it launches, it goes from sea level in Florida through the upper atmosphere to vacuum. And when it does that, things are going to get cold. And if you started at high humidity, the fairing is not airtight. It's going to equalize air pressure. And when it equalizes air pressure as it's going up very rapidly, that means condensation is going to form on the outside of your satellite. And worse, condensation is going to form inside your electronics. So they had something that they sent up to space. And by the time it got to space, all of their cameras, lenses were all fogged over in the vacuum of space. Where'd the water come from? Well, you launched from Florida, where there's high humidity. The humidity got inside the fairing, equalized, and then as it went up into space, it evacuated when the fairing opened up, and all that moisture went inside your craft and condensed on anything that was cool, like the glass of your lenses. So they had to let it sit in the vacuum of space until all the water slowly evaporated out. So you got to think about the pressure changes, the humidity changes, temperature changes, launch vibrations. Once you get up into orbit, there's all sorts of radiation. You're above most of the atmosphere, so you're not protected from the ultraviolet of the sunlight. You have to think about those things. When you finally do come back and burn up, you have to make sure that you don't have any like really hard metals or spherical chambers or things like that that won't burn up, and no hazardous materials. You don't want it to come in through reentry and explode. You'd rather it just melt away. You have to think about batteries. When you put the batteries up there, what kind of chemistry are the batteries using? Little things. And what happens if something goes wrong? You have to have either redundant systems or backup systems or failure scenarios in case, lots of different things go wrong. How do you recover? The best case recover is, it'll burn up in a few days anyway. So this is where the middlemen come in. If SpaceX is going to charge you $300,000, maybe you can break that apart and charge 30 different companies a slice of that $300,000 to cover SpaceX's costs, plus your own margins, your own revenue. So, if I could launch a satellite for $20,000 and it was limited to being under 10 pounds, and it had to be, half of a 1U CubeSat, maybe there's something I want to do that's that small. But by doing it at that price point, you have a better guarantee that I'm going to do that. But I'm a noob. I don't know anything about satellite launches and satellites. And I need a middleman to help me through all that. So the picosat and the nanosat satellite producers are going to rely upon these middlemen that are experienced in space satellite technology to act as the go-between, the middleman between you wanting your satellite up there and the rocket launch vehicle going, please isolate me from all the newbies. I don't want to have to deal with their inexperience. So you have these companies that will extract out their margin collectively over a large number of satellites. And this is where public and private universities with some donor backing can all of a sudden start, having schools in one semester launch from a bunch of different schools, small satellites. And if the price keeps coming down, then maybe someday individuals who want to test out, postulations of propulsion technologies on low Earth orbit can get something launched for a few $1,000s if it's small enough. So here's one of the bigger names that I found in outsourcing of ride sharing. Company's called MAXAR, and the last rideshare that SpaceX did, there was a whole cluster of MAXAR operated satellites that just came off the upper stage as one unit, and then MAXAR deployed the individual satellites off of that. MAXAR claims that if you want a 3U satellite, they'll launch it for $175,000. That's about half the price that SpaceX would charge you at $300,000. Now, that may be because SpaceX gives them a finder's fee and makes some margin that way. Essentially, the price is coming down, but it's not come down enough. But if you just went to MAXAR's site and said, I want to launch a 50-kilogram satellite, they'd charge you a cool $1.210 million. It's less than if you wanted to buy the satellite launch facility yourself, but it's still pricey, or you're still good money. So if you're a NASA science program and you're not given a big budget by NASA, you got some of the small slivers of NASA's budget, you can't afford to have your own dedicated launch rocket, even if it's a SpaceX Falcon 9. So what you do is you go to the NASA Science Mission Directorate, and they have a rideshare office within the SMD, and you talk to them, and maybe they can cut you some slack and launch your satellite as a rideshare within NASA aboard a Falcon 9. But if you can't afford that, then there are even smaller rockets that NASA can use out of the Wallops Island facility in Virginia. They're operated by the Goddard Space Flight Center, and they can launch for you. And if you have even less money than that, talk to the NASA Goddard folks at Wallops. They also launch lighter than air balloons. So you may not make it to LEO, but you can make it to the edge of space. So over in the European Union, the European Space Agency, they have a student ride-sharing small satellite program. And here's a collection of students as well as their mentors. And you can see like there's three 1U CubeSats sitting on the table there. You can see the relative size of them. And the name of their program is called Fly Your Satellite. And they have experienced satellite designers and operators that will help students to learn how to put satellites into orbit. Now, why would they want to do that? It's because today's students are tomorrow's commercial industry and space program workers. So they can learn as they come up so that by the time they graduate in their technical venue in college, they can already be space savvy on launching satellites and they don't make any oopsies like, was that metric? I don't remember. Was that metric? Just do it all metric. You don't have a problem. So there's a privately funded small satellite educational program. There's a group called the National Center for Earth and Space Science Education. It's a collective project of the TIDES Center and the Arthur C. Clarke Institute for Space Education and that company NanoRacks. So they have a vested interest in growing the next generation of satellite savvy professionals from students. And they have their own funding program. And it's called the Student Spaceflight Experiments Program, or SSEP. And so if you're a private university or even a public university, you may reach out to SSEP, and they may have funding where if you can't get your satellite launched by the Fly Your Satellite out of the European Union and you can't get it launched by NASA, maybe SSEP can add you to their funding and launch a whole bunch of different satellites all at once. So who's looking out for us when all these satellites want to get launched? Well, there are international regulations. The UN has some on how your satellite's supposed to burn up. There are standards bodies for radio communications, the International Telecommunications Union, and the IEEE has standards for satellite buses and structures. The U.S. government has FAA rules and FCC rules that thou shalt be conformant to, otherwise you don't get approval for launch. There's the company that's actually going to be launching the rocket, the SpaceX or the Rocket Lab or whatever. And then there's the middlemen, the ride-sharing companies like MAXAR. So if you break the rules or your satellite isn't in full compliance with something, your satellite won't be approved for launch by any one of multiple of these things, because you have to pass all the gates or you can't fly at all. If you did something that you shouldn't have done and you don't pass and you can't launch, they're under no obligation to refund your launch costs. You may get a piece of it back, but there's some fixed costs that they have to go through, because if your satellite doesn't launch, but the other 109 do, the launch still costs some money. So you want to have, if you're not aware of this stuff, you want to have an experienced company like a MAXAR or somebody that will provide the subject matter experts. Or you saw the European Space Agency, that university team of students had mentors that had experience in the satellite industry. So they're very valuable to do that. So if they want a certain amount of money for their expertise, probably going to be well worth it. But what if you have something come up that you missed your milestone? You missed something along that long list of things you have to check off. You missed your launch. Well, if it's something small and they're forgiving, and maybe your students, maybe they'll just bounce your launch to the next launch date, which may be months to a year from now. And it's only if the next launch has room for you. They might charge you some kind of bounce fee or bump fee to get you into that next flight, particularly if you did something stupid that was your fault, you didn't follow the rules. If you're working with a launch services middleman and that rack that all your satellites go into, if they have a problem, there may not be a bump fee, and you just get bumped to the next launch beyond your control. So the same delay holds true if it's the middleman that misses the date, or the booster launch provider misses the date, or the launch complex has some problems, or a weather delay. You just missed your launch. Now, if you were launching something that's going to have enough propulsion to get it outside of Earth orbit to, let's say, go to Mars, and you had a window for when's a good time to launch from Earth to Mars, if you miss that launch window, you may have to wait 2 years until Earth and Mars are close enough again. Think about this as a school program. If you are taking a semester course or a 1-year course where your electrical engineering or your space engineering degree is critical to you getting your private satellite launch, and you miss towards the end of a semester, or you miss and the launch is postponed 6 months, you may have to take an incomplete. You may not graduate. You may have to come back next year at your cost through no fault of your own, or if you did something stupid through your own fault. But those are the kind of delays that happen. But if you want to make your satellite even easier to deal with, maybe you only want to deal with your sensors. These packaging companies exist. They'll actually sell you, it's a fully operational CubeSat minus the sensor that you want. So all of the electronics, the battery, the solar panels, the navigation, the orientation, all of that's part of the package. And all you have to worry about is, did you want like a radio detector, a light sensor? Did you want a camera? What did you want added to the prepackaged satellite? And if you look at the cost of the prepackaging, it's probably going to be 2 or 3 times what you think it would cost you to build the satellite on your own as students in a metalworking shop. But they know a lot more about it. You're working with a proven satellite package with a proven satellite deployment middleman. So the costs for doing this stuff, you're going to recover it on the fact that you have a higher probability of actually getting it launched. You focus on your sensors, on your mission, and let the packager work on the actual satellite, and then let the middleman do the deployment part, and let the rocket launch company do the rocket launching. So let's say you've got one of these CubeSats, and you want to get it launched. And this picture is of the fairing halves open on a Falcon 9, and you can see all the different little satellites in there. But if you look up towards the top, you see a couple of them that are that CubeSat size, and then one that's a long CubeSat. There's a cylindrical column that goes up the center of the fairing, and then there are attachment points they call ports. And if you are a large enough satellite, you get a port all to yourself. If you're a small satellite, you get a bus bar attached to one port, and then you're attached to a sub port on that bus bar. Now, all of this stuff has to be securely attached so that it doesn't wiggle all loose and fly parts all around inside the fairing as it launches. So there are standards for doing this kind of stuff to make sure that your fly-by-night satellite's not going to damage a multi-million-dollar satellite. And look at the fairing halves. They're kind of sealed, but they're leaky. So humidity on the ground, atmospheric pressure on the ground, as it rapidly goes up, it's going to rapidly reduce the pressure, and you get condensation, and you just have to deal with that. Cabling. How do I plug in? So I've got my port. I want to plug my satellite into the port. It's not a 115 volt AC outlet. It's a DC outlet. And it's probably a giant round connector that has a spring-loaded clip that will separate when your satellite separates to go into orbit. But not every one of those connectors can be unique. They're all after a standard. So there's an organization called IPC, that no longer has an acronym. It's just IPC. When they first started out decades ago, it was the Institute of Printed Circuits. Nowadays, they're the go-to source for wiring harness standards. So the Wiring Harness Manufacturers Association is a part of IPC. And if you want your satellite to go up into orbit, you follow the WHMA wiring harness standards. And that includes like connectors and hold down clips and what the wires are made out of so that they burn up properly, so that when they do burn up, they don't create like noxious gases that pollute the Earth's atmosphere. And all that stuff is part of the standard. So if you can buy a packaged satellite that is all fully conformant to that stuff, easier. But whatever you're going to launch, it has to be conformant to all these standards that you, being new to this stuff, have never heard of before. Don't learn by trial and error. Pay a packager. So let's say your satellite is attached to one of these ports, and now it's the upper stage is now at its orbital position, and your satellite needs to be kicked loose. You can see here on the right, that's probably a half-ton size satellite, and is this giant round metal thing. You can see the wiring harness beneath it and the specific hold-down clips. Now, what will actually happen is there'll be a release of this collar, and then a giant spring will go and push the satellite off the vehicle, and that's called deployment. So when you watch a Falcon 9 launch and it says, we're going to deploy the satellite now, and deployment, and you don't see like, where's the rocket motor? Is the rocket motor going to like flame out? No, because that would hurt all the other satellites that have yet to be deployed. So they just use springs. So the electronics just releases a little latch, and by the collar opening up on the port, the spring can now shove your satellite out. And you look on the left side, you see this long bar and a bunch of little small satellites attached to a bracket. When it releases this entire bar full of satellites, and then they spring launch off of that once it gets far enough away from the capsule. But all that stuff, there's standardization for it, and you have to be fully conformant to it. Otherwise, you're not going to fly. And then you have the, as they like to refer to it, rapid unplanned disassembly. Spacecraft go boom, RUDs. But even if it doesn't go boom, even if it kind of gets almost up there, but you have a rocket engine failure, so it doesn't make it quite to your target orbit, and your satellite's propulsion's too anemic to like boost it further, so you have failures. Nothing wrong with your satellite except the fact that it burned up sooner than you want. So all these things can go wrong. They're just unexpected. You plan for the best, hope for the best, plan for the worst. So if you have a very expensive satellite, you're probably going to buy insurance from like Lloyd's of London or a company like that in case your satellite go boom, or in case your satellite fall back and burn up, or has a malfunction or whatever. Different levels of insurance. But if you're a research project that doesn't have much budget money, or you're a student at a university, you can't afford the insurance. So you just try for the best and cross your fingers that nothing goes wrong and you actually get it done, because you can't afford the insurance. Everyone's probably heard of the Goldilocks bed size story. You know, this bed's too small, this bed's too big, this bed's the right size. And ride sharing, you can have the same thing. SpaceX has this very large rocket called Starship, and it has a nose that's supposed to be able to open like a clamshell, and there might be many hundreds of small satellites that can come out of that thing. But in order to amortize the total cost of a launch, you have to pack it jam full of satellites. Well, if you have to wait until you get it jam full of satellites before you can cover its launch cost plus your revenue goal, you may not launch one of these ride shares on a Starship, but every other year. So it can launch multiple bigger ride shares. So let's say if it can launch 100 tons, you might be able to launch a bunch of 2-ton satellites very easily. Now, you could fill it up because those satellites are going to be bigger, so it can launch more often. But you wouldn't use a Starship for the very smallest of satellites. It's just too big. And then there's the other end, the too small. Rocket Lab and Firefly have smaller rockets that don't carry as much payload, but they can do the micro, the nano, the pico, and the silicon satellites, and they have to wait until they get it full too. Now, if they're smaller and your nose cone's smaller, you can fill it up faster. But they may not be a big enough company to launch the rockets as often as a SpaceX. So, Rocket Lab may launch 2 or 3 times a year, whereas SpaceX launches rockets once or twice a week, does rideshare every 3 or 4 months with 100 plus vendors on board. So these may be too small a rocket. And then there's the just right size. This would be the SpaceX Falcon 9. Rideshare wasn't a big thing. Maybe it was in the back of some people's mind, but when they first came up with the Falcon 1 and then the Falcon 9, they were intended on having enough payload capacity to launch to geosynchronous orbit good-sized satellites. And when they found out they couldn't do it with the Falcon 9, they created the Falcon Heavy, which is 3 Falcon 9s strapped side by side. So you had a Falcon 9 core and 2 Falcon 9 side boosters, and that they can launch, very big satellites to geosynchronous transfer orbit. But if you just take the Falcon 9 by itself, you can see how the fairing bulges out and is actually larger in diameter than the rocket body itself. It's just the right size. If you've got some medium-sized satellites, you can probably launch half a dozen of those. If you design your satellites like Starlink to be flat and you can stack them and put them on a rider where they're like fan out as they get spring-loaded ejected, you can launch 20 satellites that are fairly capable all on a single launch. Or if you're doing ride sharing and you launch the smallest of satellites with a couple of bigger ones, you can launch 110 satellites in one launch. That's very profitable. And with SpaceX, they can do launches from Florida or California. So you have 2 different orbital paths you can put yourself in. You can go polar, or you can go, I guess that would be longitudinal, the other direction, a normal orbit. SpaceX has got enough customers coming in for rideshare that they can afford to farm some of it out to companies like MAXAR to keep the rocket full for the rideshare program. And then comes in the student funding. I didn't know this until I started digging down the rabbit hole, but there is an annual small satellite conference. And this is where the middlemen vendors offer their solutions to small corporations and educational programs to get grants for covering the cost of the educational satellite launches. So this is actually their 38th year, August 3rd through 8th, earlier this month, that in Utah, they had this event where you had companies that actually had trade show booths because they were small satellite companies offering prepackaged satellites, or there were rideshare companies like a MAXAR that were offering to package your satellite for you and get it launched on board a Falcon 9. I don't know that SpaceX was there exclusively selling Falcon 9s, but I wouldn't put it past them. But this stuff is big time, as the saying goes. So there's a convergence of satellite sizes. You can see SmallSats, CubeSats, microsats, nanosats, picosats, and silicon sats. You can see the satellites are growing in capability, becoming specific, unique purpose, and getting smaller. So you can launch more of them more cheaply. Propulsion systems, biggest rocket kind of stuff, you'd use mixed fuels that when you mix them, they would combust, and that's how you get it. And then they went with things like hydrogen peroxide over a catalytic converter, and that would produce steam, which would be used for propulsion. They've gotten even fancier, and even the space shuttle was using this, called hypergolic fuels. This is where you just flow the fuel over a catalyst and an igniter, and it's kind of like a diesel truck engine. It will run as long as you keep the igniter running, and then when you shut the igniter off, it shuts off. But SpaceX has taken that to the next level, and they just have a compressed tank of liquid nitrogen, which is very easy to put lots of it in there. And then they have bleed valves, and they just use that for their orbital maneuvering. They use compressed nitrogen. But a tank is big. And if you've got a CubeSat, that would be too much for you. So you have to get down into the ion propulsion. And then it's a matter of how expensive is the gas. Xenon is rarer than krypton or argon, so it's going to be more expensive. But the NASA deep space probes that use ion propulsion, they'll use xenon gas. SpaceX, when they wanted to use their Starlink satellites and get them up there, they said, Ion's a good way to go, but that xenon's too expensive, and they went with krypton. Now, krypton is not as heavy molecularly as xenon is, but it's far cheaper. And they took that convergence down another point and said, let's use argon. You wouldn't want to be spewing out a bunch of argon down on Earth into the atmosphere because that's toxic to humans. But out in the vacuum of space, a little bit of spritzing argon every so often, no big deal. But argon's far cheaper and more plentiful than is krypton or xenon. Improvements in propulsion. Nowadays, they've taken that one step further, and for the very smallest satellites, they actually have a small block of iodine compound, and they melt it with heat. And then they can use that to squirt it out. So as they heat the iodine compound, it expands like 400 times, and that's how you get it to make a propulsive force. But they've even taken inkjet technology, like inkjet printer, and they use plastic polymers, and they use the equivalent of an inkjet nozzle to just, move their little satellite. Solar sails, like I said, it was good for a demonstration, but nobody's using a solar sail because how do you attack it in space? But now they're looking at high altitude atmospheric electrostatic propulsion, where you actually take the small amount of gas molecules that are at high altitude, low Earth orbit, and then you compress the hell out of it, and now you can make that your ion propulsion fuel, so you have no fuel tank. And then eventually they'll get smart and try radiation reflection pressure, and essentially LEDs and reflectors. Should they ever solve the propulsion problem and they get the satellite size down smaller, it may be to the point where you can now start having exclusive launches again because the payloads are so cheap. You can afford the price of the launch. But it also means that you're going the other direction, and you can put more rideshare on there because the satellites are getting smaller, the propulsion's getting easier to do, lower price, smaller. And now you can have maybe even high school or middle school students that are doing rideshare on top of rideshare on top of rideshare to get even high school programs to launch satellites. Got to start training them early, but they still have to follow all the rules to get their satellite into orbit. So even if you were doing it yourself, you'd still want the middlemen in there to make sure that you have easy access to getting your satellite up there. So in conclusion, there's lots of hoops to jump through, and likely some unexpected add-on costs, complications, certifications. And so ride sharing is a way of solving those kinds of things to make it less expensive to get smaller and lighter weight payloads into low Earth orbit for a limited orbital duration. Given the corporate backing of these sorts of things, you can now get less experienced people launching satellites, even university students, and even some well-funded high school programs to launch satellites. If you're a student in high school, and as your last semester in high school, you can say, that was my satellite that I worked on with 20 other students, but that was our satellite, and it went up there and it made some unique measurement that fed back into NASA that became Earth sciences observations. That's a real feather in your career cap to say you did that when you were in high school. I mean, it's good enough to say when you were at university and you did that kind of thing. That's really good because you're about to be hired by a company that can pay you more money because you're experienced. Someday you'll get a ride share on top of a ride share on top of a ride share, and you'll have silicon sats that the average do-it-yourselfer using a packaged solution can modularly add on sensors and just submit it at a fixed fee, and it'll eventually roll up and wind up on a launch vehicle and get out into space for a few days. You might be able to try out new technologies as a hacker, so to speak, as a do-it-yourselfer. I want that day to happen because then I can try out, I don't know, radiation reflection pressure for satellite inertial propulsion. And a couple of pages worth of links. And as usual, the PDF I sent around has all these as live links, and there'll also be live links when I post this for the public on YouTube. Introduction or description area. And if you're curious about the airlock that was added for launching small satellites, that's the Bishop airlock. Okay. So, any questions about satellite ride sharing or small satellites that I didn't cover?
Yes, I
Yes.
have one. How
Okay.
small are they now, these satellites? How the smallest ones?
They're about the size of a playing card and about as thick as a slice of bread.
Hmm.
That's
And
that's
what
called
sort
a
of shape would they have?
they've given up on making these things round like Telstar decades ago. Nowadays, because they're in the vacuum of space and they orient themselves, they can be any shape.
Hmm.
And so something that's just, the size of a playing card and the thickness of a slice of bread that's an entire satellite nowadays.
That's amazing. Huh.
Yeah. Now, obviously, it's not a satellite that's going to go to geostationary orbit or go interplanetary. But if you want to do monitoring of something very specific for a few days to maybe a couple of months, that's all the satellite you need. If you want to test out a particular kind of sensor, you've created a new sensor or some new computer electronics, and you want to see how well they do in the radiation hazard of space, why build
Hmm.
an enormous satellite? You build yourself a silicon sat, you put the sensor in there, you get it launched for maybe $100,000,
Yeah.
which sounds
But-
expensive, but it's certainly way
No,
less
it isn't.
millions of dollars.
Yeah, it's amazing.
Yeah.
It's
Yeah.
very cool. And
Progressions,
how do we?
progression.
How are they retrieved, or if they are retrieved at
They
all?
are they are not retrieved. They just fall back and burn up.
Hmm.
Now
Okay.
they don't have a controlled reentry point. They just burn up in the upper atmosphere. They don't pose any hazard to aircraft, and they don't come down in large enough pieces to even worry about where they're going to land because they
Hmm.
burn up with enough friction that the plasma ablation, plus the fact that they monitor what kind of metals everything's made out of, they purposefully design it so it will burn up very nicely.
Yeah. Yeah. The levels are of course assigned, but how are they controlled that they keep their level?
Um, by design of the satellite, by testing of the propulsion systems,
Hmm.
you know, you're supposed to do ruggedness testing and on the ground propulsion testing and all that kinds of stuff.
Hmm.
If you buy a prepackaged satellite from a satellite supplier, and then you go through a middleman for the actual ride sharing program, and then you go through a SpaceX to get it launched, you're piggybacking on multiple levels of experience that it's all going to go well.
Yeah. Amazing.
Uh, Now, if all of a sudden there's a new rocket propulsion technology where you, as a hacker, can launch something to low Earth orbit from your backyard, um, be afraid, be very afraid, because then all bets are off. And people will be launching satellites connected via Wi Fi. That's why they have all these international regulations and standards is they knew the day was coming when it would get so cheap that anybody could do it. Think of these electric vertical takeoff and landing aircraft that are out there now. The FAA is in a real panic over anybody can build one of these things. They just get like, eight quad motors together and they create they weld together an aluminum frame and they put a plastic desk chair seat in it, strap themselves in, use a joystick and a homebrew computer, and they're off flying. Um, yeah, there is actually an FAA regulation that allows you to do that, but you have to pass the FAA certification, even if you're going to be flying it yourself as an untrained pilot. Your aircraft has to pass
Oh
certain
yeah, sure.
decades.
Oh,
Now,
yeah.
that's a lot less than if you wanted to fly two people on board. But yeah, if you want to fly for like 30 minutes or less at 60 miles an hour or slower at an altitude of 150 feet or lower, um, there's a lot of rules that go by the wayside.
Oh yes. Oh.
So you see these eVTOLs, the one that's over in Italy is very popular. It's like $100,000, and they've sold out of 3 years worth of production of them. Now they're only producing about 60 per year, but at $100,000 a piece, 60 per year, and they've sold out 3 years worth of inventory, that's a good business because there's a lot of people that have disposable income that don't mind paying for it. And, you know, that's just for flying around. Imagine if you could put your own satellites up. Yeah, the people that have the disposable income, few $1,000,000, have my own satellite up there. Cool. Now, I can have it stay over my house all the time. No, that would be geostationary, and you wouldn't be given an orbit approval for that. I can have it go over my house twice every hour and just take a picture of my roof. You wouldn't be given permission to do that because there are already satellites that you can freely access those sorts of pictures. You have to have a purpose, a research or observation, scientific purpose for it.
Hmm.
How does something the size of a playing card communicate with the ground?
On special radio frequencies, they have little like whisker antennas that boing, pop out. So it's the size of a playing card and the thickness of a piece of bread, but it has two little like spring-loaded high-tech alloy antenna whips that pop out, and they use VHF radio because given that they're low in orbit and they're going by very quickly, you don't need a fancy radio. You know, a few watts on the ground talking to a few hundred milliwatts in space is more than enough. But what frequencies? The FCC will tell you what frequency you're allowed to use. There are reserved frequencies for small satellites. So yeah, when you think it's the Wild West, it hasn't been the Wild West for decades. Now, if someday there's a propulsion system where you can launch things to low Earth orbit from your backyard and it didn't require burning fuels and stuff, someday if there's an easier means of anti-gravity, yeah, they're going to be freaking out over it about as freakish as they do the EV tolls at the moment.
Will be mayhem up there.
Yeah, yeah.
How high are they in general? What's the level?
About 500 miles.
500 miles.
Yeah.
It's mighty interesting.
Yeah, like I said, it's probably something people haven't heard of before, but there's a lot of business activity involving small satellites. There's a lot of money to be made, as the saying goes. And the rules that you have to follow are pretty much in concrete already. And if you don't follow them or you miss a milestone on that long list, you don't fly. So don't be afraid of it.
That's great. Thank you.
You're welcome.
So using a slingshot wouldn't work to launch these things, huh?
No, but there is a company that is trying to do it with a spinning rotor that has a rocket on the end of it. And there's a problem. They have a giant spinning rotor, kind of like a centrifuge. And instead of spinning flat, it spins at an angle.
Oh.
Then when the rotation is fast enough, they let loose the rocket and it goes and breaks through a plastic covering because the chamber is in vacuum. So they can spin it faster. And as soon as it goes through the plastic covering, it dramatically drops in speed because you have the air rushing in,
right,
inflating the vacuum. And it's only going so fast when it goes out. And when it goes out, it doesn't have any rocket propulsion. It's just using, it's called spin launch. It's just using the force of it being thrown up to put it into low orbit. Now, it's gotten past the Kármán line, but it hasn't gone into orbit. It loses so much velocity exiting from vacuum into air, and then its direction is not all that controllable because if you think of a hammer throw at the Olympics, there's a wide area where the hammer is going to land. And it's because when you let go of it, you have a certain amount of rotational force that you've imparted on it. And when you let go of it, there's some of it that's still in what you just threw out there. So it doesn't go directly out all the time. You try and release it at the right time. But if you release it a tenth of a second too soon or too late, it's not going to be here. It's going to be over there. It's going to be over there. Same thing with the rocket.
Mm.
When you release it and it goes out through that port, it could get a little bit of side motion to it, and you may not make the orbit injection that you planned on. So I think it's, me
The
personally, I think it's a false start.
torpedo launcher be something, if it works in underwater at deep depths to launch torpedoes, couldn't you launch these little satellites out of a spaceship with a torpedo launcher?
The problem is that the torpedo launcher, the way it works underwater doesn't work the same way in air. They use essentially chemical propulsion, where you mix seawater with propellants and it produces basically hot steam out the back, and that propels the torpedo, or it rotates a turbine and then the turbine has a propeller and that runs it. There are also, if you've watched the high-end amateur model rocket launchers, they can get 50, 60 miles up easy, because they're building rockets that are a good 8 inches in diameter, and they're maybe 12 to 20 feet tall, and they've got 3 stages, so they can do a pretty good job, but they can't go to orbit.
I one of the things that I noted was when they put ships together during World War II, they used a special type of screw that had like a quarter cut in it.
Yes.
So you could screw it one way, but it couldn't unscrew the other way. Would that kind of thing be practical to try to
No,
shield
no, because the vibrations are too great. On board a ship, you have vibration, but the vibrations are more smack, like wave action. On helicopters, there's enough vibration in the rotor assembly that any bolts they use to hold things together, like on the pivots, the bolt goes through and there's a hole in the end of the bolt, and then there's a nut, and there's
A
a
wire.
nut.
It's wired in.
Yeah. So you tighten the nut down, and that lines up the 2 holes between the bolt and the bolt shaft, and then there's a pin that goes through, and you bend the pin open. So the nut cannot unwind even under vibration.
Do the same thing with any aircraft, same thing.
Yeah. I don't know the actual engineering term for it, but I just think of it as captive nuts.
Mm.
that makes sense, yeah.
But that's the kinds of things you have to think about. Is also, if your rocket is going to be a liquid fueled rocket, there's less vibration than if it's going to be a solid fuel rocket or a liquid fuel core with solid boosters. When you are running a liquid fueled engine, you spin up the turbo pumps and then you start your propulsive force, and it's a constant pressure fluid going into the combustion chamber. If you're a solid fuel booster, the rubber-like solid that's burning does not burn uniformly. It burns kind of like in chunks. And as it burns in chunks, and you have a lot of that force coming out the back end, you get a lot of vertical vibration from the solid boosters. They used to complain about that when the space shuttle was going up, that the difference in vibration between when the solids were attached and you were lifting off from the launch pad, and then the boosters separated, it was like, the vibration from hell is over. And now you can take the normal vibration, and by comparison, it wasn't even a hardship.
Cool.
How I learned about all this stuff, Scott Manley on YouTube, a good resource for knowing how rockets work. Also, The Everyday Astronaut's a good one too.
Super.
Okay.
Right.
Comments or questions before I stop recording?
Nope.
Hearing nothing.